Hello, everyone. Welcome to lecture 16 on finite element method. As always, we have a short review of 1D FEM. If you remember, we had this map. We said we would start from a differential equation that would be essentially our strong form. Then you derive the weak form from the strong form. Then you compute the approximate form, and eventually we want to do the numerical integration. That is something that we want to do today. About the sources of approximations, we mentioned that there are basically three different sources of approximations available in the finite element method. We talked about that. We also mentioned that the strong form or the differential equation that we are interested in solving is usually a second order differential equation like this in 1D, and that is the governing equation of mechanical systems in, let's say, in structural mechanics and elasticity. That makes sense. And the procedure to go from the strong form to weak form was by multiplying by test function and integrating over the domain. And if you do that for a strong form here, you get the weak form that we have here. Then we did this example together. So we used this as the strong form. And now for that one, because of its simplicity and because it is 1D, we actually also have an analytical solution which serves as a reference to compare our numerical solutions. Then we solved that problem also using the weak form for different approximations. These are a few linear approximations, and we learned if we have a quadratic approximation, it fits nicely to the analytical solution. And then based on what we learned, we had this, let's say, updated map, which is essentially the same thing that we had at the beginning. You have this second order differential equation. You multiply by W, integrate over the domain. You get the weak form, and then you integrate that weak form piecewise. You come to this discretized form, and we also learn to do approximations to come to this approximate discretized weak form using the shape functions or hat functions or 10 functions. In order to learn that approximation, we started with this example, and we mentioned that these shape functions or hat functions, they look like this. So they look like a hat or a tent. And they have this nice property that they basically have 1 at their nodes and 0 at other nodes. By the way, this type of approach or this type of weighting, if you like, this is, by the way, this is something like a weighting, right? So it's like you would say you have the maximum weight of 1 at a node and then weight 0 elsewhere. So this weighting is also associated with the name Galerkin. I just write this thing. So it's like a Galerkin or Galerkin weighting of the approximation. So, but it's essentially an approximation, or is a method, or is a way of approximation. And then based on that, you can write your displacements as a function of those hat functions. But also remember that these are displacements, and we mentioned that we use this thing that we call Bubnov-Galerkin and isoparametric concepts, meaning that if this is the same with u, we use the same approximation. Well, let's say we use the same approximation for x, which is the coordinate itself, and then w, which are the test functions too. And we mentioned these shape functions, they can be easily constructed, whether it's linear, quadratic, or cubic, and we showed some examples of this using, let's say, plotting function in MATLAB. And then we came to the same example using those test functions. We calculated these, let's say, the polynomials, the fitting polynomials, and it seemed like a very neat way of approximating a function or a polynomial. Then based on what we learned, we came back to this example that we had from the beginning. So we know this is the strong form, we know this is the weak form, and now we want to test it for, let's say, one-piece linear, two-piece linear, and one-piece quadratic using what we learned. And then you can see if it is one-piece linear, you get this one, and then I don't know, if it is two-piece linear, you also use the shape functions, and then now you have two pieces. But later in this lecture, we also learned that these two pieces are basically can be treated as two single pieces and assembled together. And we summarize the difference, which was basically in the previous approach. In the first approach, you are looking for the coefficients of polynomials. In this approach, you are calculating the nodal displacement. So the unknowns of the approximations are the nodal displacements, which is very nice, meaning that if you solve your system, you get the solution that you are looking for immediately. And then we also tried that example with this, let's say, one-piece quadratic function. And we learned that the stiffness has this nice structure, and motivated by that, we came back to the, let's say, the strong form, and we tried to see if we can connect that to the stiffness that we had learned through this course using the approximations. And this is basically the summary of that. We talked about this. So if you have your strong form here, you can calculate the weak form of that like this. And now here F's are basically the forces at the two ends of the structure. The only thing you need to do is now to calculate this W prime and U prime using the test functions. And we learned if you use a one-piece linear approximation, it's going to look like this. So all the integrals, they look similar in a way. So it's integral over the domain. And then component 1, 1 is n1 prime, n1 prime. Component 1, 2 is n1 prime, n2 prime, and so on. And the system that you are dealing with is basically K U equals F. This was a linear approximation. If you did a quadratic approximation, it's also similar in a sense that the system is this. Now, because it is quadratic, you have three forces or three nodes at which you apply forces and displacements. And basically, your stiffness matrix would be 3 by 3. So this was the summary. And based on that, I'm going to now write what we learned in a sort of compact form, and we use that as motivation to what we want to do next. So the general structure of a stiffness matrix, of the stiffness matrix for 1D, and again, when we say 1D finite element, it basically now means a truss, a 1D element in a 1D space. Okay, so it's 2 by 2. If you have two nodes, it's 3 by 3. If you have three nodes, but you can always have that rotation. Remember, we also had that rotation that we learned at the beginning of the course. So if you have that matrix, which is, I don't know, 1 minus 1 minus 1, 1, this is for a truss like this. Still, you could do the rotation game and you can calculate it for an angle theta, and then you get the same stiffness in a 2D. That rotation step doesn't change. So I'm not going to talk about that. I will only talk about, let's say, the part that we did. So it looks like this. Let's say K, your stiffness matrix. In terms of dimension, it's always node per element times node per element. And usually this factor EA, it comes in front of it. So you end up with a matrix which is of the size node per element times node per element. Okay, so this would be node per element. Now, as I mentioned before, usually this thing is, let's say, node per element times problem dimension, and that thing again times node per element times problem dimension. So if your problem is 2D, so if your truss is not in 1D space, then you need to also account for the problem dimension. Okay, but for now, this means that if you have a linear truss, let's say, in 1D, the stiffness would be 2 by 2. In 2D, the stiffness would be 4 by 4. Okay. And if you have a quadratic truss, then in 1D, it's going to be 3 by 3. In 2D, it's going to be 6 by 6, and so on. And if you had 3D, it's going to be 9 by 9. Okay, so that's that. Now, if you look at that matrix for, let's say, for a 1D linear truss, also you remember from what we just showed, it's going to look like this: integral from alpha to beta. The first component would be n1 prime n1 prime dx. The second component would be n1 prime n2 prime dx. This would be n2 prime n1 prime dx. And this would be n2 prime n2 prime dx. And also, again, you can see that it is symmetric. So the symmetry is clear here. Okay. So this would be your stiffness matrix for 1D. For a linear truss element. Now I will repeat this thing for a quadratic truss element. And as I said, you have already seen the big picture, so I think it makes sense to you. I'm going to just duplicate this slide and now reconstruct the same thing for a quadratic truss. And as you can imagine, most of what we have written does not change. Only now you get a third row and column. Let's have alpha and beta here. Okay, so And then again, you can imagine this thing is symmetric. I don't know if you can see it, but also the determinant of this is 0, but that is more difficult to see. But it is true. So that would be quadratic truss element. Okay, so if you look at both of these, it seems we can write something like that. So let me just write it and see if you agree with that. I can say that every component ij of that stiffness matrix K is EA integral from alpha to beta Ni prime and J prime dx. Okay. So this obviously holds in this picture. I'm going to just copy the same thing and bring it to the next slide here. And here you can see also that the same thing holds too. Okay, so that Kij is EA prime and J prime dx integral from alpha to beta holds. Okay, so this is our next mission basically. Instead of writing these matrices from this point on, instead of writing these matrices in this large form, we write it in that, let's say, index form, which is much more compact, but it has the message. And then we don't have to keep saying it is linear or it is quadratic or something. We just work with the components. So if it is linear, then those i's and j's, they would be between 1 and 2. If it is quadratic, the I and j would be between 1 and 3. So that is the, let's say, the message here, that in this example now, Kij is simply integral from alpha to beta. You have that EA, but I'm going to also keep it, let's say, here outside, but you can imagine this is a constant, it doesn't change much. Ni prime and J prime dx. Okay, so Ni and Nj, if you remember, they are functions of your coordinates. Okay, they are functions of x. So this, remember, Ni is a function of x. We actually learned how to write it in terms of a function of x or the coordinates. Nj is also a function of x. That means Ni prime is also a function of x and Nj prime is also a function of x. Maybe you can also imagine if this is linear, maybe Ni prime would be just constant. Okay, but that is not the key message here. The key message here is that Ni prime is eventually just a function of x, and Nj prime is also a function of x. So basically what we want to do is to replace this thing with a function of x. So I'm just going to call this it's an integral from alpha to beta, but it's going to be a function of x eventually, okay, for simplicity. Okay, we don't want to keep repeating these i's and j, but the goal now is to evaluate this integral. Okay, so we want to integrate this, and once you integrate that, then you are done. Okay, so everything that we have from the beginning until now, it brings us to this integral. So the next goal is to evaluate this integral. And obviously, when I say evaluate, this means usually for us, it means approximate evaluation. Okay, so you can imagine if we wanted to do what we do together here, and we actually analytically we wanted to calculate the integral, we didn't have to do this additional step that I'm going to talk about. The idea here is to approximate that and to do that numerically. Okay, so okay, so from this point on, we have, let's say, a shift of problem. The problem is simply this. Let me see. Okay, so the problem is numerical integration. We want to integrate a function using numerical methods. So to keep things sort of different from what we have done before, and then kind of making it look independent, I'm going to say this is an integral from a to b instead of alpha beta. Let's call it a to b, f of x dx, and we want to learn what is that. Okay, now we do this for different polynomial orders. For now, for this first example, think of it as being linear. Okay, so let's say f is linear, which is not too bad. Okay, it's not a very wrong assumption. We can think of it of being polynomials of different orders. Now, if f is linear between a and b, and you want to integrate f in that domain, so let's say this is point A, this is point B, and I can imagine that, or I'm sure some of you have a shortcut to this problem, but I don't want to use the shortcut because when I increase the order of f, the shortcut doesn't work. So we need to go through a systematic version of it. So let's say at A, you know you have f of A. At B, you know you have f of B. And basically what you want to calculate is this integral, is the area underneath this f, right? And as I mentioned, this is basically a trapezoid. You know the formula for the area of the trapezoid. That is your shortcut, but that is not gonna work in general. So we need to do it as if it's a mathematical problem, and we derive what we need to do. So to start this, we need to write that equation of the line. Okay, so you know you have f of a at a and f of b at b, so that we should start writing the equation of the line itself. So f of x is what? F of x is So you remember you usually say it's like mx plus b, so it's like a linear function. This is basically what we are going to do using the coordinates we have. So m, this slope of the line here, would be fb minus fa divided by b minus a times x minus a. Again, if a was 0, or if it passes through the origin, it would be mx plus b, like we usually do. But in this case, it's more like this. Okay, so this is the equation of the line. You know how to write that. Now let's integrate this. That's what we want to do eventually. So if you integrate this from a to b, you would get fb minus fa divided by b minus a. So from this x term, you get x squared divided by 2. From a term, you get minus ax. And here you just get an x. I'm going to just write that like that. So it would be 1 over 2x squared, let's say from a to b. Then from the x term, you get that slope term, ax from a to b. And then from fa term, you just get fax. Make space a little bit. Plus fa x from a to b. Okay, and then you can imagine if the function gets more and more complicated, it doesn't matter. You can always use this integral. And what I want to emphasize is to look at those, let's say, limits of b and a that they keep repeating. So if you look at the first one, you would have 1/2 of fb minus fa divided by b minus a. B minus a squared minus, now you have fb minus fa from the second one divided by, again, b minus a. Now you get
b squared minus a squared, right? Not b minus a squared.
yes, thank you very much. This is b squared minus a squared. Thank you. So that then the next one is a times b minus a, and the last one is f of a b minus a. All right. Now, if you look at what we have, and thanks to you, you just see this. So it's b squared minus a squared, which is also b minus a times b plus a. Okay, so it's that identity you have. So from that, basically, you can omit the b minus a, or let's say that b minus a with this one, this b minus a with this one. So the next step that you would have would look like 1/2 of b plus a. So that you would have something which would look like b plus a divided by 2. Now fb minus fa, so that's the leftover from the first term. The second term would look like a. Now fb minus fa plus fab minus a. All right. So this is not too complicated, obviously. But as I mentioned, the idea is to do this for this very, very simple case, because when it gets quadratic and higher order, all of a sudden it's difficult to identify these terms and relations. It's good to do it first for this and see what we do. Okay, so now that you have this, you can take this term out. You would have fb minus fa for the first two terms. Then you have b plus a divided by 2 minus a. So that would give you b minus a divided by 2. Okay, so that gives you b minus a divided by 2 fb minus fa. And then the last term is fa times b minus a. And now if you look at it, you can combine these two together and you end up with b minus a divided by 2 fb plus fa. Okay, so this is what we have, and this is just the pure integration. Okay, so nothing fancy about it, nothing new about it. Now you can imagine if you just bring the 2 to the first or to the second integral, you can write it like this: f of b plus f of a divided by 2 times b minus a. Okay, this is what I wanted to have from the beginning. Now, why is this interesting? This is the integral, and remember, this is an exact integral, so there is no approximation here. This is the most important thing that I want to emphasize on. That if you look at this term, the first term is the value, or is just the function f at the coordinate in the middle. Okay, at the middle coordinate. So this is exactly that function at point fa plus b divided by 2. And this is the length of the domain, b minus a. Okay. So again, it's not a huge surprise that we ended up with this, because eventually this is just the area of that trapezoid, and we expected something like that. But let me just make it clear here that now it looks like that. It seems like I am telling you this point, a plus b divided by 2, is a very interesting point. because if you evaluate the function at that point and you multiply that value, so that is the value of the function of at that point, and you multiply that value by the length of the line, so here you get the area, which, looking at the picture, it makes so much sense, because this thing is basically the area of this rectangle, okay? Or it's basically telling you that these two areas are canceling each other. Okay, so maybe I just say this area is usually, again, this is for you. The usual formula was f of a plus f of b divided by 2, or that's the way we remembered in, or we learned in school before, right? So multiplied by b minus a. So the way you learned this in school was always to add these two together, divide it by 2, and then multiply it by this height, basically, or width in that sense. What I'm trying to say is that that's correct. Obviously, it's the same answer, but a better or a more suitable interpretation for us is not to look at it as 1/2 of f of a plus f of b. It's to look at it as f of a plus b divided by 2. That is the correct way of looking at it. Now, why is that so important? And I'm emphasizing on it because basically what does it tell you? It tells you if you evaluate the function at only one point and you multiply that by the length of the domain, you get the exact integration. Okay, so this is the key message here. Let me just clean this up. So basically what we are doing here is to say if f was linear, so if f was linear, like we just said, that integral of f of x dx from a to b is just b minus a, that's the length of the domain, times f of a plus b divided by 2. So there are a few points here. It basically tells you that, instead of integrating, you evaluate. So this is evaluation of f only at one point. Okay, and maybe you can think of that first term. I mean, we just called it the length of the domain, but it could be some sort of weighting for the domain. Okay, so we will come to that, but let's call it length of the domain here. Now, this is an exact integral on the left-hand side. So you can imagine if you have this exact integral, first of all, in a numerical code, you can never calculate it usually. I mean, you can say it is a sum over, start evaluating that function and then do it as a sum. And then, I don't know, if you have thousands of pieces between A and B, finally you numerically integrate that. So that is the usual way of numerical integration, right? But you can imagine that's a very, very expensive way of doing this. Here, you just evaluate it at one point. It's not a summation over 1,000 little pieces. It's just evaluation at one point. But the important thing for you, and the key message here, is that this is exact integration. Okay. So we did not introduce any approximation. We reduced, let's say, the computation time significantly, because instead of an integral, you have just a single point evaluation. But it doesn't mean that we introduced an approximation. It's exact. And that's the idea. I want to tell you that there are let's say there are a few cases that we can do exact integrations by just identifying the value of a function at a few points. So not even an approximation. All right, so here is the question. This was a linear function, right? And it turns out that for a linear function, you can write the integral as the value of that function times the length of the domain. So the next question is, what if it was quadratic? Then we want to play this game for higher order polynomials. Do you get the idea? Just intuitively, it seems that it should be possible. So maybe if it was quadratic, there is a point, or maybe 2 points. So if it is linear and 1 point is enough, maybe if it's quadratic, 2 points would be enough. And maybe if it is cubic, 3 points would be enough. Which is not correct, by the way, what I just said. We will see it's even better than that. So we will see that if it is quadratic, 2 points are enough. And if it is cubic, also 2 points are enough. Okay, so it's even 1 order ahead of the polynomial. Okay, so this is the next thing we want to do. We want to know if f was now a quadratic function, what could I write here if f was quadratic? Instead of linear, could I write the length of the domain times evaluation at some points or not? And then again, the short answer is yes, but it won't be 1 point if it is quadratic. But now, because I want to, from this point on, we want to keep looking into a lot of these functions, and then these a's and b's, they keep appearing. I am going to assume that the domain is not from a to b, is from -1 to 1, for simplicity, okay? It's just a mapping, and later I teach you how to transform that mapping. That's just the change of variable, but then it allows us to, to tabulate this in a more unified form. So instead of integration from a to b, let's say now we have an integral from -1 to 1. Okay? So the next question we have is, what would be integral of, let's say, g? And instead of x, I'm going to use a different letter c here. Okay, this letter is called c. The c. So we want to see what is that from -1 to 1. If g was quadratic, Now, a quadratic G, or a generic form of a quadratic function G in terms of Xi would be C1 Xi squared plus C2 Xi plus C3. Does that make sense? It's the same problem. We just want to do a numerical integration, but we want to change the domain from -1 to 1, so that you can because you can imagine I want to do it for quadratic, cubic, and higher orders, and then I want to give you a specific coordinates for this. So those coordinates between -1 and 1, then they are more symmetric. They look nicer, but it's always just a mapping to go from let's say from AB domain to -1, 1 domain. That's not a let's say that's not a crime, really. You can do that. Okay, so this is what we want to do. All right, let's do the integral. We are at 9:20, but I think it's a very exciting point. So let me just do the integral. It doesn't take long. I do the first step because yeah, the whole message I do it after the break, but let me just do the first step first now here. So this integral would be integral from -1 to 1 C1 C squared plus C2 C plus C3 dxc. Now, if you integrate that, it would be 1/3 C1 C cubed plus 1/2 C2 C squared plus C3 C from -1 to 1. And if you do that integral, then you get this. You get 2/3 C1 plus 2C3. All right. So this is your integral. And as I said, this is so far it's just an exact integral. There is no approximation on that. Now, what can we say about these things? It's almost impossible to see the message, to see what I want to say here from the answer. But I'm going to do this little intermediate step. So I will add and subtract 1/√3 times C2. Okay. And I do that because, remember, we want to kind of identify this with points on the function itself. But these two, they do not have C2. So somehow we want to introduce a C2 into it. Okay. And it turns out that if you just add and subtract 1/√3 C2, then what you have in front of you, you can write it like this. Instead of 2/3, I would say 1/3 C1 plus 1/3 sorry, 1 over square root of 3 C2 plus C3. That would be the first term. And then the second term would look like 1 over 3 C1 minus 1 over 3 C2 plus C3. Okay. Now, if you look at this and this and compare with that, maybe you can understand why I did this intermediate step. This thing is exactly G at 1 over square root of 3. This other term is G at minus 1 over square root of 3. So it turns out that if you just add the value of the G at 2 points, 2 magic points, okay? So these points are very good points. They are not just any point. Then you have the answer. Okay, so I would say this is G at 1 over square root of 3. And then the other one is G at minus 1 over square root of 3. Does that make sense? So we use this nice property that here Xi comes in power 2. Here there is no Xi. So basically, because this term is proportional to Xi, is a linear term in Xi, if you had plus minus, or let's say if you had plus minus in Xi coordinates, they will cancel each other. So you can imagine that points, or those 2 points, one of them should be on the right-hand side in the plus side, one of them on the left-hand side. So basically, if you wanted to do this integral, as we mentioned, from minus 1 to 1, assuming that this is, let's say, 0, these 2 points, one of them is somewhere here, one of them is somewhere here. It's sort of symmetric with respect to 0, which also makes sense. Okay. So let me just summarize this before I give you a break. So it turns out what we have learned so far is this. This integral is G 1 over square root of 3 plus G minus 1 over square root of 3 if G is quadratic. So I put this here, and I duplicate it. I put one there. And this thing is just G at 0. Well, it's 2 times G at 0. Remember, the first one is just that area of the trapezoid, right? So if it is between minus 1 and 1, that length is 1 minus 1, which is the 2 here. And then the point in the middle is just 0, okay? So if G is linear, this is the way to go. And if G is quadratic, this is the way to go. Okay, so it's not bad. It seems that there is some sort of structure to it. Okay, so you can play this game. If it is cubic, and this is the nice thing about it, is it's exactly what's going to happen. So these 2 points, they not only work for G if it is quadratic, they also work if G is cubic. So even if you have a cubic function or cubic polynomial, and you want to integrate, you can use this. Okay. So this thing that we do is also referred to as a Gauss quadrature formula. And these magic points, they are called Gauss points. Okay. So basically, you would like to find the Gauss points for polynomials of order n. Okay, so that's the question. So where are these Gauss points for any polynomial of order n? That's the question. How can we just increase this? Okay, and you can imagine there there has been many or there have been many studies on this, and these info or such informations are available. Okay, so I will give you some of these points after the break. But before that, let's have a break together. It's 9:30 now. Let's have a 10 minutes. So I see you at 9:40. All right, so we are back. So as we discussed before the break, the idea is to have a numerical integration for polynomials of different orders. And as I mentioned, what we do, the method that we are talking about is, let's say, a quadrature rule or Gaussian quadrature rule, and the points are Gauss points or quadrature points. So for numerical integrations, as you can imagine, there are different methods, but this thing is the so-called quadrature rule. And as I mentioned, the points, those magic points, they are usually called Gauss points, but also simply quadrature points too. Okay. So what is this quadrature rule? Here it is. The quadrature rule basically tells you the following. It says if you have an integral from -1 to 1 of gc dxc, you can write that as a sum over some coefficients alpha I times the value of the function g at specific points within that domain. And this sum runs from 1 to what we call GPE, and GPE stands number of Gauss points per element. Okay, so this is basically is number of Gauss points per element. All right. Now, what is the order of the polynomial that you can capture with that, or how many Gauss points do you need? The relation for that is the following. Gauss points, or the number of Gauss points, GPE, must be larger equal P plus 1 divided by 2. P is the order of the polynomial. All right. So let me just sort of write that for a few polynomials here for simplicity. So let's say you have linear, quadratic, cubic. Okay, so if you have linear, quadratic, cubic, and maybe fourth order and fifth order polynomial. So maybe I write it like a table almost. The first column is polynomial order. So P here. If it is linear, polynomial order is 1. If it is quadratic, it's 2, cubic 3. Well, these are obvious, 4 and 5. Then based on the formula that we have just on the corner, then Gauss per element, if it is 1, so it's 1 plus 1 divided by 2, then it's 1. You need 1 Gauss points. If it is 2, it's 2 plus 1 divided by 2. You need more than 1.5, so you cannot have half a point. So it's 2 points. So for quadratic and cubic, it's going to be 2 points. So it's 1 point, 2 points, 2 points, then 3 points, 3 points. So how are the coordinates of those points? And so the next thing you want to know are these alphas and CIs. So for the first one, Xi, there is only one Xi. So Xi1 is simply 0. And alpha 1 is 2. Alpha is like a weighting factor, okay? But you remember, this weighting factor is basically related to the length of the domain. So in our usual integral that we did at the beginning, it was just the length, b minus a that we had there. So this is, you may call it weight factor. I'm not using letter W for this because we have used W for test functions. And so alpha is just standing for weight factor. Now, if you have quadratic or cubic, that means for both of these, we have just one set. Then you have C1 and C2 to be 1 over square root of 3 minus 1 over square root of 3. These are your 2 points. And just in the sense of the order, let's start from left to right. So minus 1 over square root of 3 maybe is the first one, and then let's say plus 1 over square root of 3 would be the second one, and the alphas are equal. Now alpha 1 is 1 and alpha 2 is 2. I'm sorry, alpha 2 is also 1. Okay, so you can see that the sum of alphas is 2. Okay, so as I said, this is like a weighting factor. So it basically tells you if you have a domain of the length 2, how much weighting would you put on which point? If you have only one point here, all the weight, all of the 2 comes to that 1 point. If you have 2 points, it's shared half and half. Okay, you will see now that if you have 3 points, the point in the middle, it gets more than the other two. So if you have 3 Gauss points, then the coordinates are C1, C2, C3 equals minus square root of 0.6, 0, and plus square root of 0.6. Now, alpha 1 would be 5/9. Alpha 2 would be 8/9. And alpha 3 is, again, 5/9. Okay, you can see if you add them up, eventually you get just 2. But the point in the center, in the middle, it has more weight to it compared to the other 2 points. All right, that's all of numerical integration, really. We wanted to do numerical integrations for polynomials. This is up to a polynomial of order 5. That is enough for our purposes. I will send you tables with far too many points. Let's say I will send you with a complete table with higher order polynomials, but this is more than enough already, I guess. All right. So this is numerical integration using quadrature rule so far. Do you have any question? Great. So there is still one thing we need to do. We just learned how to integrate a function that is from -1 to 1, or is defined from -1 to 1 and integrate from -1 to 1. But remember, the question was a function that was from A to B. Okay, so that mapping is still missing. Okay, so we learned this. This is very nice. And we keep that on the corner. Okay, great. We have this formula, and that is that's very useful, obviously, and we keep using it. But the question was, or the starting point was, what is the integral of f of x from A to B? This was the question. I mean, we know what to do with this, so we need to transform this to something that looks like -1 to 1 of gc dx. Okay, and if you do that transformation, then you can use the formula that we learned before. Okay, so that's the key here. You have done these transformations in different forms in your, let's say, in your academic life. I can give you an example. For instance, if you had, I don't know, sinus 2 theta d theta, I'm sure you did that transformation. I don't know, you call this thing u, and then you call this thing, I don't know, 1/2 u, 1/2 du, and then you did the integral or something like that. So you have done these sort of transformations, okay? But this is a slightly more intricate compared to what you have done before, but also it's more systematic. So we have learned how to do it. We didn't specifically talk about it, but we already have a very, very powerful tool to do this. Okay, so from now on, we call this X domain. So let's call this thing X domain. We call the X domain physical space. Okay, This is the real domain. This is our dimensions are there. And then that thing, that Xi domain, you call it natural space. So the idea is to find a mapping from a physical space to natural space. In other words, if I want to sort of draw it, it's like this. It's like you have a physical space, let's say here, A to B, and you have your natural space from -1 to 1. So that would be your C space, that would be your X space. What you want to do is to find that mapping. So if I know how these points are connected to each other, then you have that mapping. You can imagine the center point, or let's say 0 in C domain, it goes to A plus B divided by 2 in the X domain, right? So the center goes to center, ends go to, and that is like a linear mapping, what I just told you. So a linear mapping would be like that. You can imagine you can have quadratic mapping, you can have non-uniform mapping, by the way. This picture that you see is like a linear uniform mapping. But that is the idea, basically. You want to connect these two spaces point by point together. So what does that mean? That means you want to find X as a function of Xi. So what is X as a function of Xi? And if you have this, by the way, if you have this, remember in the integral, here you have f of x, right? So if you had x as a function of x, then f of x would be f of x of Xi, and that would be your basically g of Xi, right? So that transformation is automatically done, because then this would be just a function that is only a function of Xi, right? And also, if you know x is a function of Xi, then you can easily calculate dx in terms of dxi. Okay, so really the question is, what is x as a function of Xi? This is the question we want to answer. And also, as I mentioned here, the physical space or X domain is between A and B, and natural space or Xi domain is between -1 and 1 here. Okay, so how do we do this? Remember, the question is, how is X related to Xi? So we have already done something like this, not exactly in this sense, but we already have a very powerful tool to transform something to something. So remember before, when we talked about the shape functions, what did shape function do for us? previously. So we said, for instance, if you have u, you can write it as sum of ni ui. Now, because ni was a function of x, remember ui is, these are just numbers, right? So these are, let's say, prescribed numbers. These are values at nodes. So if we did that, you end up with u as a function of x, right? This is what we had done before. At the beginning of this lecture, I think I also showed you again that slide. Here. So remember, we can have values of a function at specific points, and then you can calculate the function as a function of x, right? It could be a linear or it could be a quadratic function. So we have that nice tool, and now we are going to use the same tool, but now in the, let's say, in the natural space, in C space. If you do that, then it's just that instead of approximating u, previously you approximated u, now we want to approximate the space itself, x. That's all it is. So what I'm trying to say is that you can just say this. You can say x is exactly the formula that you have below. It's ni xi I equals 1 to, okay, I write it p plus 1. Again, p is that order of polynomial that we had. So you see what's happening? So basically, I'm telling you what you can do is, and by the way, this drawing maybe is misleading. The mapping would be the opposite, right? So the arrows should be from X to C space. It's 1-to-1 anyway. It doesn't matter. So it could go both ways. But because we called it from physical, I think we called it from physical to natural. From physical to natural, that means the arrows go the other way. Okay. Now you get the idea, right? So here, instead of UIs, which were the values of displacements at points, now you just use the coordinates at points. So you use those coordinates, you calculate n's in terms of x's, and then you're done. So the only difference is that here you should write these ni's in terms of c. So in natural coordinates. And then you get the answer. Okay. So once you do that, then you can imagine your dx would be related to dx, but that transformation would also have a coefficient, right? Now, we call this thing J. J stands for Jacobian. Between the two space, okay? Or if you want, you can think of J as being, let's say, derivative of x with respect to c. Okay. All right, so if you do this, So if you do that transformation that we have up there, instead of your integral, which was f of c, or sorry, f of x, you would have this. So previously you had f of x dx. Now, if you have this transformation, you can say, well, this integral would be, let's say, from -1 to 1, f of x of c, well, let me just call it f of c, which in between, all you have done is to say f of x of c, so writing just x in terms of c, and then you have that j dx. Now, you can call all of this together g of c, right? And then once you have that, this is exactly your quadrature rule that you have up there. So you would go from I equals to 1 to, I don't know, Gauss per element, and so on. Okay. And then again, maybe I should be careful here. This j itself could also be a function of c. Yeah. Okay, so that's it. Does that make sense? Now, what we want to do next is to just do a few examples together to sort of digest that. Before I do that, I just remind you of these shape functions, because previously we wrote the shape functions in the physical space. Now we want to write them in natural space, meaning that they start from from -1 to 1. So I'm going to just do that. Okay, so instead of that, sorry, instead of that integral that we had up there, we have this thing. We know how to do this, or let's say the blue line is now, I guess, clear. We know how to do that. I just make it a little smaller. Okay. And what I want to show you is how to write these shape functions in the natural space between -1 to 1. So if you have the space between -1 to 1, and this is again node 1, this is node 2, your linear test functions, they will look, not test functions, the tent functions, they will look like this. So this would be n1, now this would be n2. It's exactly like we did before, except that now the domain is from -1 to 1. So if you do that, n1 would be 1 minus 1 over 2, c minus 1. and 2 would be 1 over 2 c plus 1. All right, so that's that. So the next thing you want to do is to write the test functions, not the test functions again, the hat functions in natural coordinates for quadratic functions, or for a quadratic case. Now the coordinates are -1, 0, 1, let's say, and these are nodes 1, 2, and 3. If you think of them as nodes, and then you remember, for instance, n1 would be something like this: 0 at node 2 and 3. So that would be node n1. And then if you just sort of duplicate this, but now you get this function that is 0 at node 1 and 2, but is 1 at node 3. That would be your n3. Okay, let me also change the color again. And then eventually the n2. Okay, so let's say it's that. Okay, so this is n2, and that one was n3. I think I wrote it wrong. All right, so you have these 3 functions. Now, also, if you want to write their specific functions, they will be the following. N1 would be 1 over 2 c times c minus 1. N2 would be 1 minus c times 1 plus c. And N3 would be 1 over 2 c times c plus 1. Okay, so these are the 3 functions. Is everything clear? Okay, so the next thing I want to do is to, and this is, we will do this many times. I show you the very simple example to start with, to kind of to give you an idea. But in the next lecture, we do a lot more of this. So we want to do this with an example now together. Maybe I just keep that. So let's say in this example, we use linear functions. The question, the integral that I want you to calculate is this. So it's an example. And I want you to calculate this using the techniques that we just learned. From 2 to 5, let's say 2x plus 1 dx. This is the integral we want to do. Okay, so this would be your fx. Now, the first step, as we discussed, is to do this transformation. So you need to transform your your space x to c using this. So I'm going to do that. Basically, what you want to do is to say x is ni xi. Remember, the polynomial order here is 2, is 1. It's a linear function. So you have a summation from 1 to 2. Now, the ends, you have it just down here. All you have to do is to use them here. So it's 1/2 c minus 1. And x1 is node 1 in the physical space. So node 1 in the physical space is 2. Node 2 in the physical space is 5, right? It's from left to right. So you multiply that by node 1, then you would have 1/2 c plus 1 times 5. And that would give you 1/2 c plus 3/2. Which makes a lot of sense if you just think about the two domains. So think about it this way. You have this domain which goes from -1 to 1, and let's say you have that domain that goes from 2 to 5. Okay, so this is your x domain, this is your c domain. You can clearly see the function that we calculated. It's 1/2 c plus 3/2. So if c is -1, you get 2. If c is 1, you get 5. If c is 0, you get 3/2, which is the center point. So that's exactly the first step you had to do. Now that you have x as a function of c, so you know x is 1/2 c plus 3/2. Then dx is 1/2 dc. So that tells you this is your j. Okay. Now in this integral that you have up here, you just do that. So instead of your integral, you can use these natural coordinates now. So you would have integral from -1 to 1. Instead of f of x, you would put 2 times. It's still 2x plus 1, but instead of x, you use this function, okay? So you would put the x function, which is 1/2 c plus 3/2 plus 1. So this would be now your big integral that you had. And then instead of dx, you have 1/2 dx. Okay. Now, if you look at this, you don't have to integrate it. Remember, we know how to deal with this kind of thing. It's a linear function. So all you have to do is to use that factor, which is 2, and multiply it by the value of this thing at the center point. Okay, so this would be 2 times, again, if you think of this whole thing as GC, it would be 2 times G at 3.5. And sorry, in this case, you're writing G in the natural coordinate, so it's at 0. Okay, so you insert C equals 0, then this term will vanish. Then you have 2 times 3.5, that's 7 plus 1, 8. 8 times 1.5, that's 12. Times 2, that's 24. Okay, so we integrated this thing to be 24. Now, again, because it was a nice, simple example, you could have done the integration accurately. It would have been x squared plus x from 2 to 5, right? You could have done this analytically. And now if you do that, you get, I don't know, 25 plus 5 minus 4 minus 2, which is also 24. Okay, so you see that your analytical solution matches the, let's say, the approximate solution as we expected. All right, thank you very much for your attention. I have to rush. We have a department seminar just now. Have a good day. Have a good weekend. Bye-bye.